some more. Well, let's go on a little bit and now start looking at how you would build this electrified world, which was powered to a large extent by inorganic energy such as solar. So we looked at the price of wind, and this is the cost of energy for wind, the blue line out here. Okay, and the bars out here show the annual production capacity. And what we see out here is that the price of wind energy marginally at the margin has now reached price parity in some of the wind-rich regions. Okay, and it's a very compact resource, requires very little land or water. If you look at solar energy, what you see something similar out here. You see the price of solar is dropping dramatically. This is a logarithmic scale out here, and you can see this is the price of of electricity, and here's two real points that exist right now. And so we're seeing that in 2008 and 2009, we have approached very close to grid parity, and the rate at which this is falling, we expect that within the next couple of years we will be at grid parity, at least in areas where the resources in plentiful supply. So what this also suggests is that we should be able to, in terms of land use, in terms of price parity, we should be able to, we should be able to use solar energy to provide it. The constraint, as we are going to see, is really not a supply constraint as it is for biofuels, but it's really an energy delivery constraint. So let's kind of go forward and look a little bit at that. The map out here shows something interesting. What it shows is the yellow and brown areas are solar-rich areas. Brown is very rich. Yellow is kind of slightly poorer, and the blue is wind-rich areas. And you can see that there's a geographical distribution of these. Additionally, what you see is these little squares or areas out here are where the load centers are located. And for those of you who can actually see this, you have lines in here which are where the transmission corridors are. What this is showing you is that spatially there's a difference between where the energy-rich resources are located, i.e. here and here, and where the load centers are. This is known very well, but what it tells you is that to make this economical, you have to generate energy in some place and take it from there to the places where it's needed. The second thing that you have to tackle at the same time is really the variability on a temporal scale. So what this shows you here is this red curve out here shows us what the load in California is over a whole day, and the yellow curve shows you the availability of solar energy, and the blue shows you availability of wind energy. And you can see that the three are really not synchronized in any way. And so when you start thinking about delivering this kind of energy, we end up having a major issue that has to be resolved, and that is how do you get the energy from where it is generated to where it's required. This is kind of a confusing chart, so just bear with me for a minute. I'm going to simplify this. And what it's doing is it's showing us two charts which show the grid kind of divided up into four areas, kind of like four states. Okay, so this area here where the wind generators are located is a wind-rich state, and these are three other states which do not have as many wind resources. And what you now have to do is, as you impose RPS mandates, you have to supply wind energy from the area where it's available to the other three areas, and you have to build new transmission lines to be able to do that. Now, remember from the previous slides, we showed that both the load and the wind and solar energy, have their own time characteristics. So we put all those into the simulation, and we kind of try to model and see what could happen. And what we find is that, if you have just business as usual, which means you build a transmission line every time you need to, and you build the generating plant whenever you need to, what you find is that you have a certain level of investment. Just take that as a number for now, 186,000 megawatt miles. Now, if you put some smart grid technology that allows you to control how the power flows on the network and to use areas of the network where you have spare capacity, what you find is that almost 80% reduction in the T&D investment is required to achieve the same level of capability. So this is one of the reasons why you need to be interested in what the smart grid can do. And you can see this is nowhere connected to the meter. It's really up on the grid that it's allowing us to do things that have so far not been possible to achieve. Let me kind of walk us through one more area of variability. Let's take these electric vehicles that we talked about. We saw that there's the tremendous opportunity if we could charge the electric vehicle from solar or wind energy. So we kind of next investigated what would happen if we had to do that. So we took an example of New York, a New York ISO, and said, okay, let's put 1 million EVs, which is about 5% RPS penetration for New York. And we took the wind profile that would be typical out there, which is this green curve, and we took the 1 million EVs and kind of spread them out in terms of the way they would normally, move and charge, and we came up with the charging profile, which is this black curve out here. And of course, now, if you take this under business as usual, the utility has to supply this, and we are hoping that the utility will supply this, from green energy. But to make sure that they can supply it, you actually find you need 2,400 megawatts of additional generation that the utility has to install. Not only that, but you also have to provide spinning reserves, okay, which means that what happens if the wind goes away or if something happens to generation, the utility has to be able to bring on new generation to meet the load demand. And so if you look at how the utilities have to operate under the current market structure, they have to make significant investments to guarantee that the connected load will be supplied whenever they want to, draw power from the system. So what you end up with is really under the current regulations, you end up with a lot of baggage that the utilities have to carry. Well, what we did then is we kind of converted that to a national scenario and said, let's project it out to 2030 and see what these various scenarios would entail. So first is business as usual, which we said no RPS mandates are in place. Load grows as predicted. Transportation stays in the petroleum domain. Okay. To meet load growth, we have to install another 360 gigawatts of generation. There's no renewable generation, and the emissions are kind of what we get at about 1.2 gigatons. And based on current costs, we kind of figured out what the total cost is. So we have between now and 2030, we have to spend $1.3 trillion, and we have about 1.2 gigatons of emissions, which provide the baseline. The next thing we did is where a lot of us seem to be heading right now. A lot of states are moving towards RPS mandates. 20% seems to be a very reasonable number, and we said no electric vehicles in this mix. Okay, and so what we did here is to get the 20% RPS, we had to install renewable generation. We still needed some additional generation out here to meet spinning reserve and other things. And what you see here is that you see about a 200 gigaton reduction in carbon emissions, but you see the cost went up quite a bit, almost by $800 billion. Okay, and nothing's been done on transportation yet. Well, we just talked about how we might be able to help transportation. So we said, okay, let's put EVs in here and allow them to charge at will and give a 20% RPS mandate, which is again in the optimistic scenario where many people are going. And we do the same thing, and what you find is you now have to install, you're going to use a lot more energy, you have to install a lot more generation, you have to install a lot more renewable generation, and emissions go down a little bit, but the cost could go up. Oh, well, maybe it doesn't, because what happened here? We picked up the transportation sector where we were spending a lot of money, and we could see about $3.7 billion in avoided costs. And the electric sector fuel cost includes battery costs and everything else. So you actually find out that the net cost comes down significantly compared to the other two scenarios. So that's very good. I mean, so there seems to be some overall motivation for moving in this direction.